All right, thank you, Jean. So I appreciate the invitation. It's a pleasure to be here at IPAM. And this talk will be different in character from the last one. So this is more of an optimization data science talk. I'll apologize that I didn't have time to revise slides to connect this more with non-commutative optimal transport, which is the putative subject of this program, but I'll try and at least make some sort of tenuous connection to explain why I am giving this talk in this venue. Okay, one other point of order before I begin. This is joint work with a bunch of people, Volkan Jevher at EPFL, Alpert Sever, who is at UMail, and Madeline Udell, who's at Stanford, as well as a couple other colleagues. And Alp is really the person who's largely responsible for this work. Okay. So let's get started. So I want to motivate this using a problem from data science. I'm going to go through this fairly quickly so I can focus a bit more on the algorithm and the ideas behind the algorithm. So as you may recall, there's a tension in microscopy between two goals, having a wide field of view and having high resolution. So you can see this, we have a slide here with a picture of some tissue, and you can either image the whole slide at low resolution using a 2x objective, or you can image a very small region with high resolution using a 20x objective. But if you want high resolution across the entire field of view, you have to scan the objective over the entire image, which requires a mechanical microscope setup, which can be time-consuming and can cause a lot of problems. So the question is whether you can construct a microscope that achieves both high resolution across the entire and has a wide field of view. So my colleague, Changwei Yang, and his group invented such a contraption. This is called a Fourier ptychography microscope. The idea here is that we are going to use a standard microscope objective to image the sample. So here's the sample, here's the objective. But what we're going to do is illuminate the sample from different directions and repeatedly collect images of the sample illuminated from different directions using an LED array that's fixed behind the sample. And so instead of moving an objective around, we just change the illumination pattern and collect different images. Image, 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 image. And now we use computation to take the data we've collected and produce a reconstruction, which hopefully is high resolution and has also a wide field of view. It covers the entire sample. Now, one thing I'd like to note briefly is that this setup is essentially linear. If you use approximations from Fourier optics, so the aperture is basically computing a low-pass filter. And when you illuminate the sample from different directions, you're basically shifting the frequency domain representation of the image around. Okay, so both of those operations are linear. So the overall action of the microscope is a collection of linear transformations of the sample. Okay. Now there is one issue with this type of microscope and with most optical setups, and that it's incoherent. You only collect the intensity of the light at the sensor rather than the phase. And to produce a reconstruction, you need both the phase and the intensity. And so this requires you to solve a phase retrieval problem. So this is the computational challenge behind this setup. So just to give you an idea about what's happening with these microscopes, here is a slide that has some cells that are contaminated with malaria, or infected with malaria parasites. We've collected 29 illuminations using different light coming from different angles. Each of these illuminations is 80 by 80. And then using some computational procedure that I haven't explained to you, we can reconstruct the missing phases of the image. And from that, we can compute the X phase gradient and the Y phase gradient, which are bigger images. They're 160 by 160, and you can see they're much higher resolution than the things we reconstructed. So the idea here is that by using an intelligent instrument coupled with computation, we can inexpensively collect low-resolution images and process them to produce high-resolution images. And you can see here in this cell, this ring here is evidence that these cells are infected with malaria. Okay? Whereas it's maybe a little bit hard to tell in these garbage images whether the rings are simply artifacts or whether they're actually evidence of an infection. Okay, good. So here's how this works mathematically. So we acquire a family of noisy measurements, which I'm going to call BI. Each one is a linear image of a vector psi, which is the representation of the sample transmission function, how the light passes through the slide that you're trying to image. So this is the thing you're trying to find. You can model the action of the Fourier ptychography system using a bunch of linear maps. As I told you, it really is just a linear system. And so each pixel in each one of those images is a linear function of the sample transmission function. But unfortunately, we only collect the intensity, which is the squared magnitude, rather than collecting the full inner product between the measurement vector and the sample transmission function. And as usual, because this is a scientific instrument, there is usually noise in the measurements, which we're going to model with some unknown additive errors, CI. Okay, good. So we collect these BIs, and our goal is, given knowledge of the AI, and this model to reconstruct the sample transmission function psi, including its phases. And the way we do that is to go searching among all vectors in Cn for the one that produces the same, whose apparent image under the action of the microscope produces intensities that are close to the measured intensities. Okay? So we think about running some unknown vector x through this microscope system, and we try and get a vector x that produces measurements that are as close as possible to the data we've actually recovered. We use a convex loss function to measure that discrepancy between our reconstruction and the recovered data, and we sum that over all of the measurements that we've taken. Okay? So to give you some example of what the numbers look like in that malaria example on the previous slide, the dimension of the vector x is 80 times 80, which is 25,600, and the number of measurements we've acquired in those illuminations is 185,600. So this is a moderately sized but non-convex optimization problem, which is quite hard to solve in practice, in part because these AIs are not very well conditioned. A lot of them are pointing in similar directions, and that makes this landscape of this non-convex objective challenging.
Excuse me, you don't have the choice of the AI? You cannot choose the ones which are well conditioned?
It comes from the physics, right? So you're kind of, if this is the kind of microscope you use, you're kind of stuck with it. Yeah. You can change the illumination patterns to help improve this situation, but it's still a difficult non-convex optimization problem regardless. Okay, more questions? Okay, good. So how are we going to solve this problem? So one approach is to just go for it and try and solve this nonlinear program. I will tell you that that does not work very well, in spite of the fact that people have written hundreds and hundreds of papers on it. So a different thing you can do is observe that this squared inner product can be written by expanding this as A transpose XX transpose A. And then we can rename XX transpose as capital X and treat X as a rank 1 PSD matrix. Okay? So this is a linear function of a rank 1 PSD matrix. And what we'll do now is replace that squared intensity in the objective function with AI transpose XAI, which is linear in X. Because the loss is convex in the first coordinate by assumption, this is a convex function of the matrix X. And so the objective now is convex as a function of the matrix variable. So we've lifted it from a vector to a rank 1 PSD matrix, and we have thereby gained convexity in the objective. Now, we unfortunately retain a rank constraint from the fact that capital X came from the outer product of a vector with itself, and this rank constraint is what makes the problem difficult. Okay, so this is the same problem I posed before. It's not any easier. So what do? We follow Mariam Fazel, and we replace the rank constraint with a trace constraint to convexify the problem. And so alpha is some number, which you can maybe estimate from data. And we now have a semi-definite program. We're considering X to be a positive semi-definite matrix with a fixed trace. This is a linear constraint. And we are minimizing this non-linear convex function of the matrix over all possible matrices. Now, once we solve this problem, we hope that we have achieved something that helps us produce microscope images. But X is a matrix, and we needed a vector. The sample transmission function is a vector. And what do? We compute the maximum eigenvector X star of the solution of this optimization problem and report that back. Okay? So this works. I'll show you an example in a minute. But there's a problem. We've taken an optimization problem which was nonlinear and difficult, but didn't have so many variables, and we've replaced it with a convex optimization problem where the number of variables has been squared. And so for the malaria example, the matrix in this optimization problem has 655 million degrees of freedom. Ouch. Okay. So we've taken a problem that was intractable because it is not convex, and we've replaced it with a problem that is intractable because it is an enormous semi-definite program.
Yes. Usually, when you want a low-rank solution, we'll minimize the trace, indeed.
Yes.
But here, you really want a low-rank solution, but
Yep.
you just enforce a constraint on the trace. Why should this?
It's all kind of the same. You can move these things around. You put the trace in the objective if you want to penalize it. You can switch the objective and the trace. They're all kind of the same if you adjust parameters. So here I've just chosen to limit the trace by pegging it equal to alpha. And then this is a parameter that you have to choose as you formulate the optimization problem. Yeah, but these are all reasonable formulations. Okay. So why bother with this? So here's what happens if you try and solve this nonlinear optimization problem roughly by gradient descent. This is a method which received a lot of attention, and you can see that it is complete garbage and produces results that are worse than the low-resolution measurements you collected in the first place. So solving the non-convex optimization problem is not a productive strategy. There is a classic strategy for dealing with rank-constrained optimization problems attributed to Homer and Pinato and then Burr and Montero, which is sort of convex. It factorizes the matrix variable in this SDP as a tall matrix times its transpose, and the number of columns now is a parameter. And so by increasing the number of columns beyond 1 to 2 or 3 or 5 or 10 or something, you get a problem which is a little bit convex, and maybe you can solve more reliably using nonlinear programming software. Here's what happens if you use Burr and Montero. You see a ton of artifacts in the image, which again prevent you from telling whether there's malaria or whether there are artifacts. Okay? So Burr and Montero doesn't work.
I have a question.
Yes.
You talk about image reconstruction.
Yeah.
Talking about the inverse problem because you have some measurements.
So we have an imaging system. We collect data about a sample, which is on a slide, and our goal is to take the data we've collected and reconstruct the image of the sample on the slide from the data and our knowledge of the physics of the measurement system, which has to be calibrated. So we know the physics of the measurement system, and we are trying to reconstruct the image from, so I think this is an imaging problem more than an inverse problem, really. But yeah,
in the case of the vertical flow, is it, here it's not working? Do you know if it's because it's like stuck in some local minimum or it's?
We couldn't make it work. I think that part of it is because, all of the papers on this assume like Gaussian measurements, which has nothing to do with any kind of reality. And then they prove a bunch of theorems. But in this case, it's a physical measurement system which induces certain AI vectors in the objective function, which are not a well-conditioned system of vectors. My guess is that that plays a role here.
Okay, but do you know, as an example, if the measurements with this image is consistent with the observations, or? again, sometimes has your loss converged to something small?
I
or is it
don't.
stuck?
I don't. We did this 10 years ago, so
Okay,
it's
okay,
also
okay.
a little bit hard to remember
Okay,
the
okay.
details.
Right.
Yeah. Anyway, this is a little beside the point. Tyler?
Real quick, do you get like a smooth interpolation between the rank 1 case and the fully convex case as you increase the rank, or?
I don't know. No. I mean, we do know that with Burr-Montero, if you increase the rank high enough, you should be able to find an optimal solution to the problem, where high enough is something like the square root of the number of constraints. So there is some sense in which this will give you a solution to the full convex problem. But what I am asserting in this slide is simply that if you are able to solve that convex SDP, then you could produce a reconstruction that looks like this, which is a much better image from the point of view of pathology. You see that there is very low variability in the background. You can see sharp contrasts at the edges of the cell. You can see the parasites clearly visible. So you can see the benefit of solving that convex formulation over this non-convex stuff. The point of all this was simply that large-scale SDPs arise in data analysis problems, and that it behooves you to be able to solve them. And yet the challenge in solving them comes from the fact that SDPs involve matrix variables, which have a huge number of degrees of freedom. And it is the size of the matrix, which in many cases prevents you from solving these problems with classic algorithms. Okay, anything else before I move forward? So I'm rushing a little because this is more motivation than really the content of the talk. So let me summarize what I take away from this again. For applications in data science, we often encounter large structured SDPs. The SDPs don't involve a lot of problem data because they often involve some relatively small number of measurements, and the reason you're solving this challenging optimization problem is to make the most of the measurements you have. And indeed, in many applications, the number of measurements is a lot smaller than the number of entries in the matrix variable in the SDP. Okay? And that was the case in the ptychography problem. We had 180,000 measurements, and we had 655 million degrees of freedom. Okay? So there's 3 orders of magnitude difference between these numbers. Now, there are also a lot of situations in data science where the solutions to these SDPs are well approximated by low-rank matrices. So the rank of the solution to the SDP is a lot smaller than the side length of the matrix. So here n is like 25,000, and the solution might have ranked 5 or something. Okay? So this comes up for a lot of reasons. So there are rank minimization SDPs where your explicit goal is to minimize the rank, and you do so by replacing with the trace. These problems originally came up in control theory and were studied in the late 90s. And this was really formalized in Mariam Fazel's thesis in 2000, 2001. There are also SDPs that have a small number of constraints. And results of Barvinik and Pataki show that those SDPs always have low-rank solutions, although they might have solutions that are not low-rank. And then there are certain SDPs that might have structural properties that ensure that the solutions are low-rank. So for example, in optimal power flow SDPs, the graph structure can lead to a guarantee of a low-rank solution. Okay? Now, a lot of the time with algorithms solving large-scale SDPs, the limiting factor is not the cost of arithmetic. Okay? So in your laptop, you have a microprocessor that can perform 1 billion floating point operations in a second. And that's more than the number of entries in this matrix. So it's not the arithmetic that hurts. It's the cost of storing the matrix. Because that matrix already takes like a gigabyte of memory. Yeah? And okay, we can store a 1 gigabyte matrix, but what if we were interested in a problem 10 times as big or 100 times as big? Now the matrix is 10 terabytes, and now we're sad. But even worse is the cost of communication. If the matrix is sitting on the disk and you need to move it into memory so that you can operate on it, this is extremely painful. And that's actually what kills you with a lot of these algorithms. So what you need to do to develop efficient algorithms for solving large-scale optimization problems is control storage and communication costs. The arithmetic doesn't matter as much. matters some, but these are often the limiting factors in practice. And we're going to focus on controlling storage costs as a proxy for communication costs, because if you're not storing a lot of stuff, you're maybe not moving a lot of stuff around either. Okay, so the goal of this project was to design practical, correct algorithms that solve large-scale SDPs and have minimal storage. Okay? So this was the same goal that Burr and Montero framed, but I would assert that they did not solve the problem. As you could see on the previous slide, their algorithm doesn't always work. Okay? And so our approach is going to be to design optimization algorithms that are targeted to the class of problems we're interested in, and we're going to use randomized matrix computations to help avoid the storage costs that were inherent in previous correct methods. Okay, good. So we're going to start out and discuss for most of the talk the challenge of solving nonlinear SDPs with optimal storage guarantees. We'll talk about an algorithm for doing this, and then at the end I'll show you some numerics for standard form SDPs that are based on a different algorithm that's more complicated to explain. Okay, so here's the problem template we're going to be interested in today. Okay, this is where the talk actually starts. So we're going to be interested in a semi-definite program where we have an m by n matrix X, which is positive semi-definite and has trace 1. So it belongs to the class of m by n density matrices. And the objective function has two parts. First of all, there's a linear map that takes this PSD matrix and collects some data about it. So it's going to collect D measurements, and then it's going to apply a convex smooth function to those D measurements. So the objective is two parts: a linear map A that takes the big matrix and produces a small number D of measurements, and then it computes a convex function of those measurements. Okay? So in a lot of cases, you really should think about this as a measurement process. That's what happened in the Fourier ptychography example. A is simulating the action of the microscope, which is linear. F is a loss function. In many cases, it's comparing the nominal measurements for some objective, so for some decision variable X with some observed data. And in many cases, the number of measurements is way smaller than the number of degrees of freedom in this matrix. And last, our goal is going to be to produce a low-rank solution to this optimization problem under the theory that in a lot of cases it has a low-rank solution. And low-rank solutions not only have interpretability or benefits for the problems where these arise, but they are also more efficient to store because low-rank matrices don't have a lot of degrees of freedom. Yeah? Okay. Now, as we saw before, this models problems in signal processing like the convex ptychography. It also comes up in statistics and machine learning. This was the old machine learning before the new machine learning, where people optimize things. So this is a ubiquitous problem. Okay, now here is the key idea in this work. So it is NP hard to solve the optimization problem I stated if you frame a rank constraint. Okay, so if you insist that the rank of X is smaller than some number R, where R is 1 or 2 or 5 or 10 or something, it is NP hard to even determine whether the objective value is above or below some threshold. So you can't do that. Instead, we're going to perform a sleight of hand, and we are going to find a low-rank approximation to a solution of the SDP. Is this distinction clear? Instead of trying to add a rank constraint to the SDP, we are going to solve the SDP and then find a low-rank solution, a low-rank approximation to the solution. Okay? Except that we're going to skip the step of finding the solution. We're going to go straight to the approximation. Okay? So what that means is that we're going to look for some low-rank matrix X, which is close to an optimal point of the SDP. How close? Nearly as close as the best rank R approximation of the optimal point. Okay? So if the SDP has a solution which is well approximated by a low-rank matrix, we're going to produce something that is also an excellent solution to the SDP. That's what this inequality states. Yeah?
do you have any like intuition that a low rank solution should exist?
Yes, that was the point of the previous slide, that there are a lot of SDPs that do have low rank solutions, and in fact only have low rank solutions. So it is often the case that the solutions are low rank or close to low rank, and so it is reasonable to try and produce a low rank matrix that is a good approximation to that thing that is almost low rank. And indeed, if X star had rank R, the right-hand side would be 0, and we would report something which is exactly equal to the optimal solution. Okay? So if the only solution to the SDP is a rank R matrix, we will find it. Okay? But we're allowed to relax that claim in case X star is not low rank or it's only approximately low rank, whatever. Okay?
We're finding the best or just a rank R?
We are trying to find a near optimal rank R approximation to a solution of the SDP.
Not necessarily the best rank R approximation.
It's going to be a rank R approximation which is competitive with the best rank R approximation of the solution to the SDP. Okay? So I'm giving up a little bit on finding the best rank R approximation of the solution, just a little. Okay? Maybe I pay a factor of 2 or something. Yeah? More questions? This is really the key idea here. It's a sleight of hand which replaces an NP-hard problem with one that's tractable. Okay, the way we do this is complicated, and I'll explain it, but this is really the main takeaway. Okay, questions on this? Yeah.
So if you talk about the dual of the SDP, is it also a rank 1 approximation for the dual?
If I talk about our...
For the dual problem.
We're not talking about the dual problems, yeah. Yeah.
Ideally, we will not choose article 1.
You could.
You can do it?
Sure. For sure you can do that. And then you get something which is an approximation to the maximum eigenvector of the, without, yeah. So you get something which is an approximation to the maximum eigenvector of the optimal solution up to some constant error.
In the picture you showed, when there was a need, the image was clear.
Yeah.
It was with R equal.
No, I think R is 5 or something. In those problems, because of the physics of the system, the solutions tend to have rank which is constant, 4 or 5 or something. So, and then we take a maximum eigenvector of that rank 5 matrix. Okay. All right, good. So what kind of storage bounds could we hope for? So first of all, we need some way to work with the problem data, which is, allows us to exploit the structure of the problem. So we're going to assume that the linear map is equipped with some primitive operations, which allow us to avoid working with full dense matrices and vectors. So there are going to be 2 operations I'm going to ask for. The first one is that I can apply the measurements to a rank 1 matrix. So it takes as input a vector of length n. It forms the outer product of that vector and then takes measurements of that rank 1 PSD matrix. And that is a list of D numbers because A has output of size D. And so we are going to assume that we can do this efficiently. So this is like taking measurements of, in the Fourier ptychography example, is like taking measurements of some particular sample. Okay. Second, we're going to assume that we can apply the adjoint of the linear map A to a vector Z and multiply the resulting matrix by a vector U. So what does that mean? We have some prospective measurements. We are going to form a reconstruction using the dual. So this is a guess for what the matrix is that generated those measurements, and then we're going to multiply that matrix by a vector. So this takes 2 vectors, one of length n and one of length d, and produces a vector of length n. So these are informationally simple. The degrees of freedom in the input and the degrees of freedom in the output are small. Why are these the right primitives? Well, they let you build algorithms. It's not well motivated at this point, but the basic idea is that in a lot of examples, these linear maps are extremely structured, and so we can implement these primitives directly without forming full-size matrices. So for example, in a matrix completion problem or something, this would involve picking out entries of this rank 1 matrix. But that's easy, right? So if A is a mask that reports entries of a matrix, you just pick some of them out. Dually, that would take the values of the entries, form the matrix with those entries, and then multiply that sparse matrix by a vector, okay? So these are very simple natural things that you can implement directly. Now you need M plus D storage for the output of these operations, and so you're never going to do better than that if these are the primitives used to interact with the linear map. Second of all, if we're reporting a rank R matrix as the output of our algorithm, it takes about order Rn numbers to write down that low rank solution, okay? So we're never gonna do better than Rn storage just to report the output, okay? So we're going to say that an algorithm for our nonlinear SDP has optimal storage if the working storage is the cost of using these primitive operations and then reporting the solution to the user. So D plus Rn. And that should be compared with n squared, which is the cost of writing down the m by n matrix in the SDP. Okay? So we don't want to do this. And if R is small and D is small, this might be quadratically better than the cost of a standard SDP solver that involves writing down a full-size matrix. Okay, good. So that's our goal. Now, let me tell you about an algorithm that can accomplish this task. It's called Sketchy CGM. It's based on a classic algorithm from optimization called Frank-Wolf, or the conditional gradient method. I'll give you an idea about how this method works, and I'll show you how to layer on some randomized linear algebra ideas to make this algorithm efficient in the sense of storage. Okay, we ready? Awesome. Okay, so here's how the conditional gradient method works. So we'd like to optimize a function over the set of density matrices, which, as you know, is shaped like a pentagon. And we're going to assume that this function g is smooth and convex. Okay, so here's how this algorithm works. At a given point, x, which is our guess for the solution of the optimization problem, we'd like to improve our guess. That's how most iterative methods work. So what are we going to do? Gradient descent would take the negative gradient of the objective at that point, which maybe is going in this direction. Okay? And gradient descent would take a step in the direction of the negative gradient. Conditional gradient does something else. It follows this vector in this direction as far as it can inside the set of density matrices until it can't go any farther. So it arrives at an extreme point. Now, what are the extreme points of the set of density matrices? Oh, the rank 1 matrices. So instead of updating x by moving in the direction of the negative gradient, we're going to move as far as possible in that direction. And then we're going to update x by moving in the direction of this rank 1 update. Okay? So the way this works mathematically is that we are going to find the matrix Y, which is best aligned with the negative gradient of the objective at x. And then we are going to average in the solution to this maximization problem with the current x to get the new point. But in the case of the set of density matrices, H is always rank 1. Okay? So this is great. Moreover, obtaining the solution to this problem is really just a matter of computing a maximum eigenvector of the negative gradient, which is a matrix. Okay? So we have a symmetric matrix here, and we need to compute its maximum eigenvector to find the update direction H. Okay? So 2 steps. Compute a maximum eigenvector of the negative gradient matrix, and then average in the rank 1 matrix with the current iterate, and repeat. So that's how this algorithm works, and I've written that down here. There's some particular step size schedule that makes this work. And
it's expensive, no? To find the eigenvectors of the, it's probably at least n cubed, no?
No.
N by n matrix?
No. No. We'll talk about that. It's closer to order n. Yeah. Well, order n primitive operations. Yeah. So this is much better than doing dense linear algebra. Okay, so here's how the algorithm works. I want to call your attention to the eigenvector computation, which in the case of our SDP involves an objective function, which is f composed with a. Its gradient is the linear map A composed with the gradient of f composed with the adjoint of the linear map. Okay? And so that's here. So we need to compute a minimum eigenvector of this matrix, and then we form negative UU transpose, and then we average that into the iterative, and then we repeat. Okay? So this algorithm costs you one eigenvector computation per step. It converges at a rate of 1 over t, where t is the iteration number, that is true whenever f is strictly convex and smooth. So it's an okay algorithm. Okay? Yeah,
Is
Mario.
it guaranteed that the rank does not go up if x?
It does not, and that's the problem. I don't have a picture of this in this talk, but what happens in practice is the rank goes up at every iteration, and it will continue going up. Eventually, though, the epsilon rank starts coming back down.
If the eigenvalue was used in the x in the first place, it might not, but you just
It does. The rank goes up at every step. That's the problem. You can see that at step n, x has rank n, or the n is a bad number. X has rank t at iteration t. Sad.
Sad, yes.
Okay.
And the influence of the parameter alpha here, where the traits are physical.
We're setting alpha equal to 1 for the rest of the talk, I think. Great question. It would appear here in front of h. Okay, good. So Martin Yagi had a beautiful observation in 2013. He observed that you can combine the conditional gradient method with randomized Lanczos to compute these minimum eigenvectors. So here's how this works. In conditional gradient, we need to compute the minimum eigenvector of this matrix M, something. Right now, we don't have an efficient way to deal with this matrix. But what happens in randomized Lanczos or in the Lanczos method, is that we start with an initial text vector and we repeatedly multiply it into the matrix M to form a Krylov subspace. So this only takes matrix vector products with this matrix. The randomized Lanczos method starts from a random vector omega, which turns out to allow us to prove guarantees on the behavior of this randomized algorithm from computing the minimum eigenvector. And it is a fact that the randomized Lanczos method can compute something which is competitive with a minimum eigenvector efficiently, even if the matrix has no spectral gap. It always works, and the randomization ensures that. And a key observation here is that this algorithm can be implemented with storage order Qn, where Q is the depth of the Krylov subspace. Okay? So you don't need a lot of storage to run this algorithm. You just need to be able to multiply this vector omega repeatedly into the matrix M. Okay? So Martin proposed that we should use this algorithm for that eigenvector computation, and so this avoids the n cubed costs that you were concerned about. Okay? Yeah.
Just out of curiosity, did you use anything else but the normal like vectors as a starting point?
Did we use anything else about what?
As a instead of initialization, did you use anything else except the normal vector? Maybe like in the tests, like.
No, we're just drawing it from a normal distribution, like simplest thing possible. Yeah, and that's what Martin is proposing. Of course, as you know, you can use warm starts and other things to try and gain computational efficiencies. Okay, good. So now we come to Marius's question. What happens? This is a disaster. So first of all, this algorithm works, but it only converges after thousands of iterations. 1,000, 10,000 would be typical. The numerical rank of the iterates increases without bound. Every time you add a rank 1 matrix, the rank of your decision variable goes up. And so it requires a lot of storage, and the amount of storage is unpredictable. Even if you try and be clever about this, it's kind of a fail. And so the idea that we initially had was that you can modify this algorithm to work with optimal storage guarantees. And so there are 3 ideas involved here. The first one is that we're going to drive the iteration with a low-dimensional state variable. So instead of keeping track of this matrix X and using X to drive the algorithm, Instead, we're going to look at the image of x under this linear map A, which appears in the objective. So remember, z is a d-dimensional vector, where d is a pretty small number as compared with the dimension of x. So we're going to write an iteration that only depends on a state variable z, and the state variable is all we're going to need to drive the iteration forward. Second, instead of keeping track of this big n by n matrix, which we need to solve the problem, instead we're going to compress the matrix X using randomized sketching. So instead of tracking the matrix X, we're going to track a random linear image of the matrix, which is a low-dimensional object, and we're going to update that at each iteration. So we're going to update the sketch at every step of the algorithm, and then after we've decided that we are tired of optimizing, we will unpack a low-rank approximation to the decision variable from the sketch. So the sketch has our best guess for the solution to the problem, and then we're going to unpack it from the data after we finish optimizing. So the optimization only keeps track of the state variable, which is d-dimensional, and the sketch, which is going to be something like r times n, where r is our target rank for the solution. Okay? So this is great. We have solved our storage problems if we can make this work. Okay? So let me show you why we can do this. Okay. Questions? What? Well, we can. Otherwise, I wouldn't be talking to you. Okay. So here's the first step. This is the algorithm I showed you before. What we're going to do is we're going to take the AX and write it in terms of a state variable z. And then we're going to apply the linear map to the update equation so we get an update for the state variable. This is a linear function, so that's not a problem, yeah? Okay, so let's do that. Good. So now we are driving the iteration with z, and we have to compute the gradient of f at z and do this stuff, and now our update direction is a applied to the minimum eigenvector outer. Okay, good. But look, here, when we use randomized Lanczos, we need to multiply this matrix times a vector. Oh, but that's the primitive for the adjoint. We're going to apply a star to some vector and multiply it by some other vector repeatedly. But that's the primitive that we assume that we have. A star times a vector, a star applied to a vector times a vector is all we need to run randomized Lanczos. Okay, so our primitive saves the day. We need some small number of applications of the A star primitive to implement this eigenvector computation. Here, to compute the update direction, we need to be able to apply the measurement map to a rank 1 matrix. But that's our other primitive. So these are the only ways we interact with the linear map. And they let us implement the conditional gradient method efficiently. And now the state variable just gets updated in the same averaging fashion as before. Okay? So this only uses storage m plus d, so this is great, and we're exploiting the fact that we have primitive operations that allow us to interact with the linear map A. Okay. Questions how that goes? Okay, we've forgotten something important. We've forgotten the decision variable. Okay, so this is being driven by state variable, but we don't care about the state variable. It doesn't help us. It's just some measurements of the decision variable. So we need to figure out what the solution to the matrix X that solves the conditional gradient. We need to figure out the matrix X that solves the optimization problem. And we've forgotten that. So we need to figure out how to recover that. So the idea here is that we're going to add another set of steps to the algorithm, which allows us to track the matrix decision variable using sketching. So briefly, what we're going to do is we're going to fix a target rank for our solution of the optimization problem at the beginning. We're going to draw and fix a Gaussian random matrix, which is part of the data for the sketch. And at any given time, when the decision variable is x, the sketch is going to be of the form y equals x omega. So we're just going to keep track of the product of the decision variable, the matrix, with the sketching matrix omega. So y is going to be a tall matrix, and that's what we're going to watch. So omega's fixed forever. X changes as we run the iteration. And so the sketch of X is going to change as we run the iteration. And so this random image of the decision variable is all we're going to keep track of. Now, it's clear that we can update the decision variable in this linear fashion by operating on the sketch. So if we multiply this linear equation on the right by omega, we get an update for the sketch. And so H is just a rank 1 matrix, right? So this update to this tall matrix is a cheap linear operation because H is rank 1. All right. So this is what we layer on to keep track of the matrix solution to the optimization problem. We fix a random matrix, we use it to define a sketch, and then we update the sketch of the data at each iteration. And then after the optimization is finished, there's some complicated formula that lets us produce a low-rank approximation to the solution, a low-rank approximation to the decision variable that we would have achieved with CGM. And this has guarantees on its quality. Okay? Good. And we only need order Rn storage to keep track of omega, the sketch, omega, the test matrix, and the sketch Y. Good. So that's how the sketching works. And when we add that into the algorithm, it just creates a few extra steps. So we need to initialize the sketch. We need to update the sketch so that we can keep track of the matrix variable without using a lot of storage. And then after we're done optimizing, we get tired. We reconstruct we produce a low-rank approximation of the decision variable from the sketch, and that has guaranteed accuracy. All right. So this is the code for the sketching. This is just to show you that a bare-bones implementation of this algorithm is really just 2 slides. Okay? You don't need to digest this right now. Good. And there's a theorem that goes along with this. Effectively, we're implementing the conditional gradient method. So this inherits all of the guarantees of the conditional gradient method for solving this nonlinear SDP. The only difference is that instead of following the matrix that the conditional gradient method is driving toward a solution to the optimization problem, we're tracking an approximation. And so implicitly, this algorithm computes a sequence of matrices that converges to the solution set of the SDP. And these xt are the iterates of the conditional gradient method, but we never actually see those. The algorithm computes near optimal rank R approximations x hat t to the trajectory of the conditional gradient method. So at each t, I can get an approximation to whatever the decision variable is. And the storage costs are optimal. The number of output dimensions of the linear map plus the cost of storing the low rank or reporting the low rank approximation. And so for simplicity, if you assume that the SDP has some stability properties and at its optimal point has low rank, then the algorithm produces rank R iterates that approach the optimal solution to the SDP in trace norm. The objective values for our reported low rank iterates approach the objective value of the optimal, and they do so at a rate of 1 over t. Okay? So it was like the old beer commercial. Less filling, so not so much storage, but you still get the great taste. Okay. I remember this from when I was like 8. Okay, so you can quantify the resources to obtain the epsilon optimal implicit or xt or whatever. Okay, good. Questions on the theorem? So this is Elvira.
So will the approximation be feasible, or does it matter?
No, it's so the approximation is because of the formula for this SDP, you can make the approximation feasible because it really is just a density matrix. So you can always get a density matrix out. For more general SDPs, which I'll talk about briefly in a second, the solution is not feasible. Why? 1 minute, okay, good. So I'm going to show you a couple pictures, which will take 2 minutes. You might ask whether you can also solve linear form SDP, standard form SDPs. The answer is not with this algorithm, but there's some other algorithm. And that algorithm is called Sketchy CGM. These are Sketchy seagulls. And here are 2 images. The first one is when we apply this similar algorithm, Sketchy CGM, to the MaxCut SDP. So we applied this to a whole collection of matrices off the interwebs. We compared this with all of the standard solvers, Sadumi SDP-T3, Mosaic SDP Now Plus. And you can see that the storage costs of these algorithms are increasing rapidly, and they run out of memory when the MaxCut problem is on a graph with about 10,000 vertices. Whereas this algorithm continues running until the number of vertices is on the order of 10 million. 20 million, 25 million, I think, okay? So because the storage costs of this algorithm are smaller, we can solve much bigger SDPs, even on graphs with 25 million vertices. Moreover, if you look at the runtime, these algorithms increase in runtime pretty rapidly, and then they run out of memory. This algorithm is not necessarily so fast, and it's also not very high accuracy, but nevertheless, in some reasonable amount of time, we can solve SDPs with 25 million. We can solve MaxCut problems on graphs with 25 million vertices, which amount to SDPs with something like 10 trillion variables. Okay, so that's cool. And we're actually solving these problems. To low accuracy, I grant, but these are certifiable solutions. All right, now coming back to the problem we started with, Fourier ptychography, there's a linear SDP formulation of the same thing. And we did this for a slide that has a sample of the cells infected with the Marburg virus, which is horrible. And so now we have much bigger images, so 320 by 325, 320 by 320 pixel. Sorry. The image we want to reconstruct is 320 by 320. To do so, we take 225 illuminations, so shining light on it from 225 different directions, and each of the illuminations is 64 by 64. So the SDP here has 10 to the 10th variables. So the SDP matrix is about 10 billion entries. There are about 1 million equations. And we can run this algorithm for this problem. So after about 1 minute, we run 10 iterations and we see nothing. After about 20 minutes and 100 iterations, we see nothing. If we continue for 1,000 iterations, which takes about 5 hours, you start to see an image which strongly resembles the actual microscopic image. And then after 10,000 iterations, which is about 50 hours, it's almost imperceptibly different from the ground truth. And this is all on a laptop. Okay? So in short, these ideas of looking for an approximation to a solution of the SDP and using randomized linear algebra techniques allow us to solve SDPs, real SDPs coming from data science problems, even when the matrix has 10 billion variables on a laptop. And with that, I will leave you some references and thank you for your attention these last 2 minutes.